Welcome to this video, guys, where we're going to take a look at another interesting problem from mathematics and take a closer look at the problem solving process and how it looks when you try to find a solution to a non-routine problem. So the problem that I've chosen for this particular video is taken from this book, Numbers and Proofs by RBJT Allenby. So this was a book that I picked up recently. It looks quite interesting. Some nice problems in it. Really good book by the looks of things. I haven't read it cover to cover yet, but it seems to be something that I definitely recommend to people. If you've got an interest in understanding a bit more about how proof works in mathematics. Okay, so the problem that I've chosen is from page 107 of this book, and it's question number 15, or exercise 15 from this book. By the way, guys, just before I get started, this is a fairly new YouTube channel. We've only got a few subscribers at the minute as of the time of making this video. I'd be really grateful if you'd hit the subscribe button, let other people know about this channel, and if you'd hit the like button. And it'd be really great as well if you could leave a nice comment in the comments section. Cheers, guys. Okay, so let's get on with the problem then. So the problem is, prove that there are exactly 3 positive integers n such that n factorial has exactly n digits. Okay, there is a little bit of an issue with the statement of this problem, which I'm going to come on to later. It's not something that really changes the nature of the problem. It's just maybe an oversight or something like that. I don't think there's exactly 3 positive integers. I think there's 4. But we'll come to that in due course. So before I jump into trying to find a solution to this specific problem, I'm actually going to change the problem slightly initially. Because to solve this problem, really, you need something that can do calculations for a calculator, a computer, or something, because you are actually going to have to calculate some factorials, in some cases some quite large factorials. So I was thinking about this along the lines initially of, well, once I figured that out, at first I didn't realize that that's what you needed to do. Once I realized that really you needed a calculator or something to help you out a little bit, I thought, how far could I get? What kind of progress could I make if I didn't have a calculator to hand? And I didn't really want to be doing specific calculations. I didn't have any way of knowing, without doing the calculations myself manually, of knowing what the values of the various factorials are and things like this. So I don't have any books or anything that I can just look up. All I've got is a pen and paper and my brain. And I don't really want to do the potentially quite massive calculations. How far can I get with this? And what I thought is, can I put some bounds on the value of n? Can I put an upper bound on the value of n? Because this is a common thing to do in mathematics, is to potentially try to bound find an upper bound for the number of possibilities. Okay, so we're wanting to show that there are exactly 3, 4, maybe possibilities. Even if we could kind of bound this, let's say we might say that we show that there's at most 100 possibilities. This is still progress. Okay, we've gone from all possibilities, all infinite possibilities, and we've kind of narrowed it down to, well, there's at most 100 possibilities, and they're in between these particular values of n, for example. This is a very common thing to do. So sometimes the solution to a problem doesn't necessarily come about straight away. It comes about through stages, through gradually refining the bounds on something. That can happen. So, okay, let's have a look at the problem that I suggested then first, and then we'll have a look. We'll go back to the problem as it is in the in the book. So one way that we can calculate bounds is to look at worst case scenarios. Okay. Now sometimes these worst case scenarios seem obviously not true, in the sense that, for example, one of the worst case scenarios that I'm going to assume here is that 10 factorial has at least one digit. Okay, this is one of this. It's not really an assumption. It's a fact. 10 to the factorial, 10 factorial, sorry, has at least one digit. In fact, I'm going to go so far as to assume that 10 factorial has one digit. Okay, so assume that 10 factorial has one digit. Okay, because every number, every positive integer is at least one digit long. Okay, now you might say 10 factorial, surely that's got more than one digit. Okay, but we're looking at worst case scenario. I know that, for example, 4 factorial is 24, 5 factorial is 125. So even when we get up to 5 factorial, we know that 5 factorial has 3 digits. So yeah, I could say assume 10 factorial has 3 digits. Okay, but I'm not going to do that. I'm going to go for worst case scenario, and it really doesn't make any difference anyway. Okay, so if 10 factorial has one digit, then if I multiply, then 11 factorial, every time I multiply a number by 10, then a whole number, then I add an extra digit, a 0 on the end. Okay, so if I start with a 1-digit number and I multiply by 10, I get a 2-digit number. If I multiply by 10 again, I get a 3-digit number. Multiply by 10 again, I get a 4-digit number. Okay, so remember what factorials mean. Factorial, n factorial is equal to n times n minus 1 times 2 times 1. So 11 factorial means 11 times 10 factorial. So I'm multiplying, if I think of this as multiplying 10 factorial, again, worst case scenario, by 10, then I'm adding another digit. Okay, so 10 factorial times 10 is going to be 2 digits. So 11 times 10 factorial, in other words, 11 factorial, is going to have at least 2 digits. So has at least 2 digits. Uh, 12 factorial, again, I'm multiplying by at least 10. This is going to have 3 digits. So what we can see here is 13 factorial, 14 factorial, 15 factorial, all the way up to 19 factorial. I'm multiplying by at least 10, so I'm going to get at least one more digit added at each stage. So 3 digits, 4 digits, 5 digits, 6 digits, all the way up to 19 factorial is going to have at least 10 digits. Okay, so 19 factorial has at least 10 digits. Why is this important? Well, we'll see in a second. But notice that the number of digits is not static. Okay, the number of digits is increasing as this number increases. The problem that we've got here is that because we're making this worst case scenario assumption, the number of digits, the digit is only going up by 1 each time. Here the number n is going up by 1 each time, but the number of digits is only increasing by 1 each time. In fact, it's probably going to increase by more than 1 digit occasionally in here. It's just we don't know that. We don't know where, and without doing specific calculations, we're not going to be able to figure out. Okay, so 19 factorial has at least 10 digits. So what I'm going to assume now is that 19 factorial is the smallest possible number with 10 digits, which is a 1, followed by 1, 2, 3, 4, 5, 6, 7, 8, 9 zeros. Okay, so I'm going to assume that 19 factorial is equal to this. What's that? A billion? 1 times 10 to the power of 9, whatever. I know that 19 factorial in reality is not going to be equal to this. I'm fully aware of that. But this is worst case scenario. Okay, so all we've done effectively is taken the 1-digit number and assume that we're just multiplying by 10 each time here to get this. But now what happens? This is where things start to get a little bit more interesting. Because now I get to 20 factorial. So now pay attention to the initial digit here. The initial digit, when I multiply by 19 factorial by 20, what happens? Well, I add an extra digit, but this number doubles. The initial digit will double to a 2. Okay? And now, so the number of digits has gone up by 1, and the total number of digits now is 11. So 21 factorial. Again, I'm multiplying by at least 20. So what I'm going to get is an extra digit, and the initial digit is going to double. So I'm not writing everything out. I'm just doing a bit of shorthand here. 22 factorial. I get an extra digit, and the initial digit will double. But what about when we get to 23 factorial? Again, I'm multiplying by at least 20. So I'm going to get an extra digit, because I can think of it as multiplying by 2, then multiply by 10, or multiply by 10, then multiply by 2. So I get an extra digit from the extra 0 that's going to be added on. But notice that the initial digit is greater than it's greater than or equal to 5. It's 8. So when I double this, I'm actually going to get another digit now. So think about if I've got 80, and I multiply this by 20. Okay, well, multiply by 10, I get 800. Multiply by the 2, I get 1,600. So I go from 2 digits to 4 digits. That's an increase of 2 digits. So at this stage, the initial digit goes to 6. Does it? No, it doesn't. Sorry. It goes to 1. And the number of digits goes up by 2. Aha! So what I can see now through this is that whereas here, between 10 and 19, the number of digits of the number increased by 1 each time. Now, it usually increases by 1 each time, but sometimes it's actually going to increase by 2. Okay, it's going to increase by 2 digits. That's interesting, because this always increases by 1. Okay, this number here always increases by 1. If the number of digits was always increasing by 1, then it would always lag behind. The number of digits would always lag behind the value of n by a fixed amount. But the fact that sometimes it can jump up by 2 digits means that the number of digits, which at the moment is 15, is eventually going to catch up. Okay, so they're kind of going at the same, increasing at the same rate for a while, but then one jumps up a little bit faster. Then they increase at the same rate again, then it jumps up a little bit. Eventually, they're going to level out, potentially. Or the one that was lower, the number of digits, is going to exceed the value of n at some point. So I'm not going to go through the whole calculation to find what what the bound is that we can place on this, but it might be something like 40. So by the time we get to, I don't know, 40 factorial, what we'll find is that the value of n here is going to match the number of digits, or is at least going to be less than the number of digits. Okay? Now, this establishes a bound, and I'm going to show you how that establishes a bound, because it's not forced to do, but it does. Because, let me just get rid of some of this. Suppose n plus 1, now I've got to get this right, n plus 1 is greater than or equal to 10, and that n factorial has n plus 1 digits. Okay, so then n plus 1 factorial is going to be equal to n plus 1 times n factorial, which is greater than or equal to 10 times n factorial. And because we're multiplying by 10, remember when we multiply a whole number by 10, we add a digit. So if n factorial has n plus 1 digits, then 10n factorial is going to have n plus 2 digits. So what this shows is that once the number of digits exceeds n, so here we've got n factorial has n plus 1 digits, then it will always stay above. Okay, the number of digits will always exceed n. So n plus 1 factorial will have at least n plus 2 digits. It might have n plus 3, might have n plus 4, who knows? But it's going to have at least n plus 2 digits. Similarly, n plus 2 will have at least n plus 3 digits. So once that the number of digits exceeds the value of n, there's no going back. Okay, so that's what establishes our bound here, that we can continue this table until the number of digits exceeds the value of n, and at that point there's no point in continuing anymore. We've established our upper bound on the value of n. So if we were to continue this table, it would probably, I don't know, it might take us up to something like 40. Okay, we might get up to 40 factorial before things even out. Now 40 factorial is a big number, but it does at least give us the satisfaction of knowing that any numbers which satisfy this condition, where the number of digits is equal to n, the number of digits of n factorial is equal to n, is going to be finite in number. Okay. Now it might be unpleasant to calculate 40 factorial or 39 factorial, 38 factorial, and so on and so forth, but it's not. It's at least practically possible. Even at a time, maybe a couple of hundred years ago, it might be expected that in the not too distant future that somebody, if it hasn't been done already, somebody would be able to compute the values of these numbers, and we'd be able to get a definitive answer. In this day and age, it's no problem, right? 40 factorial, computers can do this. They're still long numbers, they're still big numbers, but a computer can do this now. It's not like we've established an upper bound of 1 trillion or something like that. Now, a 1 trillion factorial, even a computer would really struggle to deal with 1 trillion factorial. But 40 factorial, no problem, right? Okay, so we've established our bounds then. So then it really becomes a case of actually start to compute the values of the factorials. So yes, you do kind of need a calculator for this. And it is just a systematic search. Start with n equals 1. You get 1 factorial equals 1. This is one that I think has been overlooked somehow in the book, because if you notice, 1 factorial has 1 digit. Okay, Then we check n equals 2. 2 factorial equals 2. Okay, that's only got one digit. No good. N equals 3. 3 factorial equals 6. One digit. No. So we calculate n equals 5. It's n equals 6, sorry. 6 factorial equals 625. That's 3 digits. Nope. And what we do is we continue until we get to n equals 22. When we get to n equals 22, we find that 22 factorial equals a 22-digit number. I'm not going to write it. In fact, I didn't even write it down. I just counted the number of digits. N equals 23. And 23 factorial equals a 23-digit number. N equals 24. 24 factorial equals a 24-digit number. And then when we get to n equals 25, we get 25 factorial is equal to a 26-digit number. So there, the number of digits exceeds the value of n. Refer back to this result. If the number of digits ever exceeds the value of n, forget it. Okay? There's no point in continuing because it's never gonna go back under. So what do we find out then is that n equals 22, n equals 23, n equals 24 are possible, are values such that n factorial has n digits, but also I would include n equals 1. I'm not sure why this is not being included. I did actually look at the solution because of this discrepancy. I wouldn't normally do this. I looked at the solution in the back of the book, and it still didn't seem to acknowledge the possibility of n equals 1. It only the solution only acknowledged these three possibilities. Don't know why. Maybe it's a little bit of an oversight. Nevertheless, that's not a criticism of the author or anything like that. It's a perfectly good book. These kinds of things happen. But that's my solution to this particular problem. An interesting little problem. Very non-routine. That's the sign of a good problem, that it makes you think, and also that there's you can kind of modify the problem. You can look at it from different perspectives, not necessarily just find a solution to that specific problem, but you can actually kind of change things within the problem, change the parameters, so to speak, and see what else you can squeeze out of that particular problem. So that brings us to the end of this video. Thanks a lot for watching, guys.